Hey there, friends from the future. I assume you're either watching this on video or catching the live stream, which may be a second or two delayed. And so you're from the future either way. Last time I had a chat on the stream, I had a chat with Dan and was Tinkerbell 101. Ended up being more of a story on bare metal provisioning 101, and then had a tiny intro to Tinkerbell. Today, we will go a little bit more in depth with Gianluca, who I will bring in here now.
Hey, hello everyone.
Thought it would be excellent to bring you on for a chat on Tinkerbell, as when going through GitHub, it's mostly your name I see again and again all over the Tinkerbell GitHub. Can you give yourself a brief introduction, and then also what your role on the Tinkerbell project is?
Sure. I'm Gianluca. I'm from Italy, from the north side, close to the Alps. So this year is not going to be a good one for skiing, but usually that's what I'm, thrilled to do at this point in time. Probably more than Tinkerbell, but yeah, I'm not going to say this on stage. I did that. Anyway, I work as a software engineer at Equinix Metal, and I did a bunch of stuff along these first 6 months at Equinix Metal. So I worked at the Kubernetes cluster API provider for Equinix Metal, and now I'm more focused on the Tinkerbell project itself. So I like to do open source. I do it like a lot I used to do it a lot in my free time. Now I can get paid to do that, so that's a good plus. And that's one of the reasons about I'm involved with Tinkerbell. I used to be involved in a lot of different projects from the CNCF, like Kubernetes, or even outside. I was a contributor to Docker previously, and in my previous life, or in my first life as a developer, when I was doing PHP, I was also involved with different communities there, because that's mainly how I learn how to program, or stuff like that. So it's good for sharing and for knowledge bump. So that's mainly the reason about why I'm so involved and around with Tinkerbell, I presume.
Yeah, certainly appreciate the contributions to Tinkerbell and other projects. You mentioned the CNCF, and I think we have some things that are new on the Tinkerbell and CNCF front.
Yeah, we got accepted as a sandbox project recently. I say that. So yeah, we made the application because as a company, it is important for us to be as open as possible with the Tinkerbell project itself. So we have a long journey as a backend first, and as Equinix Metal now, onboarding and helping and supporting open source projects with our hardware. And yeah, for us was a natural consequence to find a good way to donate Tinkerbell, to keep it open, because it's hard when when a company is so tied to a project. So we decided to apply for the CNCF incubation, and we got accepted. So now it's the start of a new journey, I presume.
Yeah, I'm looking forward to celebrating with our CNCF friends at KubeCon this week.
Yeah, that would be a good challenge. We just got accepted a little bit too late to be at the conference with a booth or as a maintainer, but next time.
Sure enough. So I had a previous conversation with Dan. Was supposed to be Tinkerbell 101, but ended up being more of the sort of bare metal 101, bare metal provisioning 101. And with the recent updates that Tinkerbell has, wondered if you could sort of walk through the instead of the why, some more of the how of Tinkerbell and its component parts.
Sure. I have to say, I didn't have any experience with bare metal provisioning before joining Equinix Metal. So all my knowledge is built on the last 6 months of my life. So it's not a long one. But having the opportunity to work with who is driving this topic in the industry, it's way easier for me to catch up. So definitely has to say, Dan gave a very good introduction about the problem itself. With Tinkerbell, we are trying to share the operational experience we had as a cloud provider with the community, mainly because as compare with a couple of years ago when everything was Intel and everything was like made from the it was way less diverse than today. Now we have ARM and AMD, RISC-V, and way more architecture, way more servers, way more companies, and it's easier to onboard all of them if we work with a community other than just ourselves. So one of the cool features that the packet host and Equinix Metal gave was the ability to use a Verizon of like servers and architectures. In order to keep doing that, being open source and onboard a community and build a community around a project is way easier. It makes everything easier. So, I mean, the topic is always the same. How do we, starting from a, not that smart piece of metal that comes from a box in a package, how do we make it smarter? And smarter means whatever we need. Like, it can be a Kubernetes cluster, that's the smartest stuff you can do, or it can be, everything else. You can run your SMTP servers, or you can run your containers, your application, whatever. The idea is, how do we make, what's the life cycle of a server when you buy it, when you plug into in the rack, and what's happened from there. So obviously in a cloud provider, there are no like people running away around with USB sticks trying to install operating systems on demand. That's not how it works. I mean, I never saw an Equinix Metal data center because COVID, but I presume there are no people running away with USB sticks. So in some way, you need to convert a request that you get from the API from the customer to a live machine. And the story is the one that Dan really well described. So it asks for an Ubuntu server, so you have to figure out where it is, and you have to install the right operating system, and so on. So Tinkerbell does all of that, or at least gives you the primitives to have that goal. And it does that with a couple of services. So I'm going to share my screen, and I mean, I decided to use my, the documentation we already have, other than, doing a presentation, because I think it's also good for the community and for everybody to use the tools that at the end they will look familiar at some point. So this is our website, and there is a documentation. And as you can see from the documentation, there are like a menu that describes a bunch of stuff. So what I want to highlight here is that Tinkerbell as a project is made of a bunch of different servers, a bunch of different services. Almost all those services are written in Go, and they run as a container. Obviously, whatever runs as a container can run as a binary. So you can get the binaries out from the container, but containers are for us the unit of work that we decided to ship at the beginning. I'm working at releasing binaries as well, but as I said, like, binaries are inside the containers, so it's just a matter of copying them out. So
can you bring your text just a little bit larger?
Yes, I can.
Perfect.
So the services that Tinkerbell provides are Tink, Boots, Higger, Ozzy, and BPNJ. So if you look at them, they are projects on GitHub. So they are mapped 101. So there is the Tink repository, the Boots repository, and so on. So if just to remember what Dan described briefly, like when your server boots, and when it boots, the BIOS have different way to look for the operating system that has to run. When it comes, there is nothing in the hardware itself, so it goes along the chain, and usually at some point it ends up doing net booting. So there is a mode that accepts scripts, And the script describes where the operating system is, so where the kernel is, where the root FS is, and from there it's able to boot an operating system. So if you look for like Ubuntu net booting, you on Google, you see that there are images that the same images served in netboot mode. So there is a kernel and an interim disk mainly. So that's what we use. So as soon as you get to the Pixie mode, you download the scripts and you get an operating system running. That operating system is not persisted, so it's not in your hard drive. So when you boot it again, it will the machine will do the same all over, won't find anything on your hard drive, and will go to the netboot and will keep doing that forever. So how do we escape the loop? We have to make we need to have an operating system that runs in Pixie mode and that is a bit smarter and will persist on disk what we want. So that's the topic we are kind of trying to solve here. And in Tinkerbell mode, we have like a Tink server that is provided by the Tink. Like as you can see here, the Tink repository provides a CLI and a gRPC server that you can use to communicate. So it's mainly, the architecture is mainly like, let's say the Kubernetes one in some way, when you have a control plane that is for us, the Tink server. For Kubernetes is the API server, and you have a daemon that runs in each node. For us is the Tink worker. In Kubernetes is the kubelet. Obviously, this is where the comparison ends. All the rest is different. Just to give you an idea about how it is designed. So when the in-memory operating system that I told you about, the one that gets downloaded by the Pixie scripts, for us is called OSI. And OSI, as you can see from the documentation, is a in-memory installation environment. So it is an operating system. For us, it starts from Alpine. And what it does, every time like an operating system starts, there is a script located in /init in the file system. And that script it gets executed all the time for the initialization. So we modified that script to start Tink worker. And Tink worker is a binary exposed by the Tink repository. What the Tink worker does, remember the Tink worker runs inside the hardware, that your target hardware, because as you get the Pixie script. The Pixie script says, okay, this is the OSI that you want to download. So it downloads OSI, it runs OSI. Inside OSI contains the Tink worker, and the Tink worker starts. That's the story. The Tink worker starts and asks to the control plane, so it asks to the Tink server, do I have anything to do? Do I have anything to do? I mean, it keeps asking this question to the Tink server, and the Tink server may say, yeah, I have this workflow that you have to run, or it will say, I don't have anything for you. So the Tink worker will keep waiting. That's the story. So you can save whatever you want in the Tink server, and the actions or what you want to do, we call them workflows. Workflows starts from a template. So you write a template, it's a YAML that says what you want to do. So you can wipe disks, you can partition disks, you can download images, and you can persist the images on the hardware that you just partitioned. So that's usually what you do, but you can do whatever you want. Those actions are just Docker containers. So you write your template, you store the template in the Tink server, and you create a workflow. And the workflow is one template for one server. So it's the situation where when you assign what to do to a target hardware. So as soon as there is a workflow for the hardware, the Tink worker will execute the workflow. That's mainly how the situation works. And all these communication are made over gRPC. And all the steps that has to be executed are Docker containers. I think we need a break now and see. Whoa. But
And so, yeah, and at this point we have so there's the Tink server, the Tink workers, and what state is the hardware in at that point?
the hardware is it is running OSI, so it's waiting for work to be done. And what happens after that is technically it is provisioned, but it really depends what you are doing. I mean, traditionally, what like 99% of the use case we saw, for example, in Equinix Metal, is that you get with an operating system persisted in the hardware. So next time that the server restarts, you don't go into the Pixie mode anymore because you have your hardware configured. So from their point in time, there is no Tinkerbell business involved anymore. From that point in time, is your server with your operating system ready to be used. So how do you move forward? So let's say that you want to clean the hardware because there is no customers that want to use it anymore. So how do you do that? This is a space that Tinkerbell doesn't cover 100% yet, but there is this project called BPNJ that is not part of the stack. It's not released as part of the stack yet because there is enough rewriting phase, let's say. But that's the project that communicates with the BMC of the server. So you have to imagine that servers are so big and complicated that there is another small servers that helps you to figure out what's going on. So if the big servers usually is hooked to memory or your RAM, your like SSD and whatever, the BMC, the small one, is hooked to more management tasks. So you can measure the temperature, the voltages for the CPUs, the consume, and there is also an API that helps you to stop and restart a server. So let's say that it's time to clean a server. My expectation for the workflow is that Tinkerbell will communicate with BPNJ and say that server has to be restarted in Pixie mode. In this way, you will be able to jump over the hard drive and Pixie will start OSI and you are in the Tink worker again. And for that Tink worker, there is a workflow that has to run. And that workflow says wipe disks. And you have your disk ready to go again. So this is the story. And there is more. So we spoke briefly about like Tink. We spoke about OSI, PPNJ. Boots is kind of the server. It's kind of the service that glues everything together. So you can think about the Tink server as the place where metadata gets stored. So in the server, you push your hardware. So you register the hardware you have. You register templates. You register workflow. You start workflows. But this is all metadata. We spoke about like Pixie, and Pixie needs to receive a script, and it receives a script from a DHCP via TFTP. So that's already a lot, but I know that Dan covered that, so I don't want to repeat that phase too much. So you get and Boost does all of that. So Boost is a DHCP and a TFTP server. So when your hardware starts, it goes to the iPXE, and usually the iPXE script says, give me, like, it does a DHCP request, and the DHCP gets broadcasted and returns the IP of the hardware and returns the iPXE scripts that we have to run. So the iPXE script is served by boot and via TFTP. TFTP is like a light FTP protocol that is very good for tiny little scripts, not for gigantic like files.
Trivial scripts.
That's it. Just the easy one, just a small one, and that's what Boost does. It does more, but like that, this is like the main competence for it. And Higger is the last service that Tinkerbell provides. And if you know other cloud providers, they have a metadata server, and the metadata are very useful to pilot provisioning from inside the server. So the metadata for AWS runs on some particular IP, so you can secure them and use them in your automation. Metadata does the same. Higgle does the same, but for Tinkerbell servers. So when you are inside a hardware, you can always, let me go here in the services. Like there is a documentation for all the services. Some of them are better documented than others. So let's see if Higgle will be a good one. But if I remember it should be good. Yeah, as you can see, and if you already know like AWS metadata, for example, GCP metadata, you will find that familiar because we implemented the same format. So from inside the server, you can do secure the Haggle IP, and you can get the metadata. And the metadata for a server usually are in JSON format, like they are in JSON format, and they contains information about the instance itself. Those instances, those information are stored in the Tink server. So at the end, Haggle goes and communicates with the Tink server, gets the right information about the hardware, and it serves you. It serves them to you in a comfortable way that you can use from inside the server. So the Tink worker can use those metadata to build smart like integration. So for example, you can, if you want to know the facility of the server when you are in the server, because you don't know that usually, you don't even know where your hardware is. So that's the situation we are all in. So you have to ask the metadata server. And this is what Higgle does. And there is documentation about the other cloud provider, so you can compare based on your knowledge if you already use them. And yeah, I mean, this is mainly an overall architecture, an overall idea about how the architecture works. I don't know if you have any curiosity to ask or whatever to point out here.
Yeah, the when looking to try things, it was has Sandbox moved along? Where are we at with?
Yeah, I mean, we have a project. It's called Sandbox, and it's documented in the setup here. So there is the Sandbox currently supports two different mode. One is in Vagrant, and one is in Terraform with Packet. I mean, we have to change Packet to Equinix Metal now that I see that. But yeah, I mean, you can use like Equinix Metal, you can use Vagrant. I usually use Vagrant because I like to have stuff running in my local laptop for some reason. So if you can follow this documentation and have Tinkerbell up and running. I'm going to move to my terminal, and I'm going to explain how the system works looking at the Sandbox project, because I think it helps to glue together in practice what's going on in there. But in general, just to give you a mood, you clone a repository, you get in a particular director, and you start a Vagrant provisioner that is the control plan that I told you before. So the control plan runs Haggle, Tink server, it runs boots, and a registry for the Docker images. Because as you remember, everything runs as a Docker image. All the actions are Docker images. And we choose that format because it's well understood by the industry. So everybody now knows how to run and build a Docker image. So for us was a piece already done that we just had to use. From there, you have to do a bunch of shell scripts to mainly set up your environment. And from there, we use Docker Compose to spin up all the services that I just told you before. Boots, the PostgreSDB, Higgle, Nginx registry, and a bunch of other stuff. And from there, you're good to run the hello world. So I think I'm going to move there. And I think I almost remembered this setup guide now. So let's see what we can do. Let me see if I remember if we are in some dirty situation or not.
You'll probably stand to size up the terminal also.
Mm-hmm.
Perfect.
Okay, so when you clone Sandbox, you are kind of in this situation without the M file. So you get a bunch of files, and you can um, do. And this is the Sandbox project contains all the glues that brings an environment up and running. So if you go on the deploy folder, you will see that there are Terraform scripts and also Vagrant. Today we're gonna go with Vagrant. So in the Vagrant directory, you get a Vagrant file, and if you know a bit about Vagrant, you know that this looks familiar to you. And it's not really complicated. Like we spin up two virtual machine. One is called Provisioner, as I told you, and it's the one that serves like Think server, boot, and all those stuff. And the second one is the actual worker. So the worker is the hardware that we want to provision. So it's the brand new server that doesn't do anything smart that we have to, empower.
And to be clear, Vagrant's not a part of the Tinkerbell project and is not required in any way, except unless you're looking to demonstrate its use without using real hardware. It's what we're using to create an imaginary data center.
That's
a virtual data center.
Very, very right. Yeah. And yeah, that's it. So when you can start like the provisioner, and you will see that there are a bunch of logs. What it does, it sets up the network for you, because the Tinkerbell, it's not a requirement. It's a good practice to have a network interface dedicated for Tinkerbell. So all the work that Tinkerbell has to do to set up the server won't collide with the internet or the private your private networking. It's just a ring used by Tinkerbell. So it does that part. It downloads all the dependencies, so all the containers for boots, for Postgres, and so on. And it generates the certificates because everything is encrypted in Tinkerbell, so there is no plain communication going on. You get everything encrypted, and it downloads the registry. We have an internal Docker registry in Tinkerbell because, it's not a requirement. You can use whatever you want. We have one because we know that usually in a data center, you tend to have your own, to be disconnected from the internet as most as you can. So having a private registry means that you don't have to go to docker.io or Docker Hub to get your images. But it means that you have in some way to get them loaded in the registry. With Vagrant on Equinix Method is easier because we have internet, so we can reach docker.io, download the image, tag the image for the new registry, and push that in the internal registry. Otherwise, you have to find your way. Usually, it involves like hard drives or whatever. But yeah, it's just a plus that you get because, as I told you before, like Tinkerbell comes from an experience that we use. It's what we use at Equinix Method, just a bit more like general purpose, let's say. We're making it more general purpose as possible. And so as you can see, it's downloading, like it's installing dependencies. And one of the dependencies is, as I said, Docker, because that's what we use. After that, what we will do, we will SSH into the server, into the provisioner, and we will start Docker Compose, so all the dependencies are up. We will register hardware. We will follow what there is in the setup guide. And I'm just going to give you, as I'm trying to do now, a bit more context around what's going on. So you will be able to kind of start from there. So in the meantime, and everything goes, I can tell you, like, we share the Sandbox directory inside the server. When we use Terraform, we copy the directory into the Terraform server. We have a person, and there is a blog somewhere on the internet that used the Sandbox project to install Tinkerbell in OVH So technically, you can use the same scripts whatever you want. For now, we just documented 2 of them, but at this stage, Tinkerbell really is like powered by hackers that goes and try and go deep in the code, because there is a lot more than you can do compared with what we documented. Mainly because we use a lot of it already, and we want to document only features that we know that we reworked and are ready to be used as they are. So there are a lot of hidden gems in Tinkerbell that we didn't document, mainly because they are not ready to be used as they are. They will come available probably in a different form.
Yeah, I suppose that's a useful for folks to know. I think Tinkerbell.org is probably going to be your jumping off point. There's links to GitHub where you can either raise issues or make pull requests if you have something that would be useful to add, and then the documentation's there, but also a link to the Slack and the Tinkerbell channel in Slack where maintainers and folks hang out. And so if you find an interesting or novel use, or have questions about any issues you're encountering, that's there's folks there most all the time.
Yeah, we also have a bi-weekly meeting with contributors that is very useful, because there are people involved like me every day on Tinkerbell, but there are also people from the community that are trying to move their first step with the project. So we are always getting demos from people that are trying new stuff, and we discuss about ongoing work. So it's a good way to kind of get the vibe of what's going on. Anyway, the setup by the Vagrant app provisioner is done, and it kind of gives you an idea about what you have to do now. So as you can see from the logs, it already downloaded like images that we already heard today. So it downloaded ThinkWorker, it started the registry, and so far. So and so on. So if you do Vagrant SSH provisioner, as described, and we go in Vagrant deploy, and we source a magic file that is a env file that now we're going to look at. So this is generated as part of the Vagrant provisioner. The Vagrant provisioner just runs a bash script that is the setup script. So if we look at the setup, this is the sandbox. There is a setup.sh that runs in Tinkerbell, or that runs on Vagrant, or runs on Terraform. So this is the script that does the setup. So if you want to use it, that's good. If you want to read it and do your own, that's also good. But as you can see, one of the steps is to generate the env.rc file. So the env.rc file is this one, and it contains the version of the dependencies we want. So those are the dependencies that we will run as part of this environment. You can change them. So if you are downloading, if you are contributing to Tinkerbell, you can build your own Docker image and replace that here, and you will run your code there. There are other ways, but this is a good way to contribute. There are also variables like the network interface. As I told you, we tend to use a dedicated network for Tinkerbell. So this is the one that it used with its host IP and Nginx, and there is the password for the registry as well. It's a facility. Those are, as I told you, there are a lot of gems that are legacy or that are close to be deprecated. So those are a few. So we load that there, and now it's time to run Docker Compose. So we do Docker Compose app/d, but you can do that by yourself. We're gonna do it together, but it's fun to see what it is actually, because that's what we can do differently compared with looking at the setup guide by yourself, I presume. So it's a Docker Compose. So what it does, it gives you it runs the containers that we depend on. So we are in the control plan, as I told you. So that is the Tink server, and the Tink server is just a container with a start policy and a bunch of environment variables. As I told you, Tink server depends on Postgres. So there are environment variable about how to configure Postgres, or there are certificates and passwords in there. It depends on two other services, so two other containers. One is the Think server migration, and the other one is the database. So those are. And also remember that there is a volume shared that is the state directory, because we're gonna speak about it later. There is a Think server. No, this is the Think server migration. So the Think server runs migration because it uses Postgres. So schema has to change, or we need to add new tables. So there is a mechanism for migration. And the first migration is the one that creates all the tables that you need. And the migration is part of the Think server. It just runs with a different environment variable that is only migration. So when you start the Think server with the only migration environment variable, it does the migration and it exits. So when you have the Think server migration, but it obviously depends on the database itself, because you have to apply migration on something. So the DB is like a Postgres. It's just a Postgres, as I told you before, where you configure the password and so on. Other than that, you have the Think CLI. This is not a long-running server. It's something that we place it there for conveniency. So you have the CLI to use. It has its own image that is specified in the emp.rc that we saw before. So if we look for the Tinkerbell, we copy this and we go into the emp file, we see that there is a reference in there. So the image that you specify in the environment file gets used in the Docker Compose one. So there is a registry, as I told you. It starts from the Docker registry project, the open source one, just with a different configuration. There is boot with its own environment variable. This is a very good way to, if you open Docker Compose by yourself, you can have a look about what runs, how it runs, and you can run it differently or try it outside from the sandbox if you need to do that. There is Nginx that serves statics file. So it serves, for example, OSI. As I told you before, like OSI it's an operating system. So it's a tarball that gets downloaded by the hardware via iPXE. In some way, we have to pull it from a source. And we have an Nginx, and the Nginx has a state folder. It's the same state folder we saw before. So when you run the sandbox, we download a bunch of files that get stored in the state directory, just for caching purpose. So there is the registry volume. So when you push all the images, they get stored and cached locally, so you don't have to download and push them all the time. And same for the web routes. The web routes are the files that get served by the Nginx, and they are used all over from boots or from the Think worker. For example, if you look at the web root MISC, there is an OSI directory with OSI. So as you can see, there are like installer. So this is the init scripts, or there are like kernels for the various architecture. So this is where OSI lives, let's say. And I presume I don't remember the top of my head, but if we look for one of these, not this one. Somewhere we should look. Yeah, this is as I told you before, like every operating system has a /init script that starts as a PID1 every time that you start the operating system. And in our case, OSI starts the Think worker. Because that's where all the magics happen. And as you can see here, this is where the Think worker starts, if I remember correctly. So because this is the init scripts that gets downloaded in OSI. And it's all served by an Nginx one. So now that we know what did I do? Docker compose. Now that we know, and there is Hegel as well, but it goes on. So now that we know what we're gonna run, we can do the command, because that's what like smart people do. They look at what they are doing, and after that they do it. I don't do that. I just do that because I'm on live stream and I have to be a good person. But yeah, that's what happens. I mean, it downloads like the containers as any other Docker Compose will do, and everything will start. So after this command, when this command is done, we have a provisioner up and running. So the brain is ready. Now we will be able to follow along and register our first hardware, that is the vagrant worker machine in this situation, and we will we create a template, and we will create a workflow, and we will start the worker to see the workflow getting executed if it works. If it doesn't work, we're going to troubleshoot it. That's also fun, I presume. So that's it. I mean, using containers gives us a lot of power already built and battle tested that we don't have to re-architecture. So it means every OZ and all the provisioner are running Docker. So it means that if you want to take all the logs and push them into a centralized location, you don't need to do anything like different than what you do normally when you do Docker logs driver, and you configure your log driver, and you have the logs shipped to Fluentd, Elasticsearch, or whatever, because the engine is Docker under the hood. So obviously,
it's I suppose useful if you have if you're looking for one particular machine. But if you're doing bare metal provisioning this way, the likelihood is there's 10 machines, 100 machines, 1,000 machines, and so figuring out either which ones failed where, or what at all's going on with them.
Yeah, I mean, that's perfectly true. And using containers and Docker gives us a lot of features that we just have to hook and glue in Tinkerbell, and we can do a lot of powerful stuff. Not only we have a runner, we have a process management, we get login centralization, and events all served by somebody else, so we don't have to do it. So that's it. As you can see, we have created a bunch of containers, and if we do Docker Compose PS, we see them up and running. All of them are up, other than the migration that is already done. So if we do Docker Compose logs-f, we should see logs. They are kind of boring because there is the registry spams logs all the time, but you can see that there is the Tink server initialization that is initializing the HTTP server and the gRPC server as well. So stuff are moving, let's say. So what else we can do? From there, we can go back to the local setup guide, make it bigger, and we are at this point. So we saw the logs. So we do Docker logs. That's where we are now. As I told you, we have to we have an internal registry that runs in the provisioner. So I'm gonna proxy the image that we will use in the workflow. So in this case, the hello world one. So I'm gonna pull the image, I'm gonna tag the image with the new registry, and we will push that to the registry. And that's it. It says layer already exists because it's using the state directory, and I didn't remove that because my network is not that fast. So I won't be able to do download, push, and streaming at the same time. That's it. That's where I live. So now it's time to create the hardware data. So in this case, we fixed the MAC address and we fixed the IP in the vagrant file. Usually, if you are on if you have your own hardware, you will have to get the MAC address and compile that. there is a proposal, but I'm going to speak about proposal later. So for now, just take it as it is. So I'm copying that and executing script. So I'm just creating the hardware file in the Vagrant machine. And now is where we use the Think CLI for the first time. So the Think CLI is a CLI, so it's a utility that you can use to interact with the server. It's a gRPC API, so there are clients, you can do whatever you want, but if you want to start quickly, you can use the CLI. And it does a bunch of stuff. So we can, in this case, we are pushing a new hardware, that is the JSON that we just specified. But if we do think help, you see that there are a bunch of commands like hardware, template, and workflows. So if we do, now that we pushed hardware, we can do, for example, hardware, and we see that there is a delete, an ID, a list. So we're going to do hardware list. And you will see that there is our hardware that we just pushed. What else? We have to create a template now. So the template, as I told you, is the way you describe a workflow. So what do we want to do? In this case, we want to execute one single task with one single action that runs the hello world image. This is the easiest one we can do. It won't do anything smarter, but it will start a container and it will run the container. And that's the base, that's the mechanism that you have to master. That's what happens. You take a container, you run the container, and whatever you run in that container gets actually executed in the target that you specify. So let's register our first template. And you register that with the CLI. So it's the same, but other than doing hardware, we do template create. And we have our first template. You can do the list again by your own. As for that, now we can create a workflow. And when we create a workflow, as I told you, we need two information. We need the MAC address and the template that we want to start for. So it's the same. Create, and we get the template ID we just created. And luckily for us, for this guide, the MAC address is fixed. So I don't need to look around for that. And that's it. We do that and we create our workflow. So now if we do Docker, if we run the CLI again and we do workflow, we can do events and the ID of the workflow to see that there is nothing happening. There is nothing happening because our worker didn't start yet. So if we open another terminal and we do vagrant app worker, and we do, I don't remember, so I'm gonna look at that. By default, the worker runs without a GUI because we run integration tests as well, so we don't have a GUI there. But if you use this environment variable and you do vagrant app worker, we should see the GUI showing up. So it's the same vagrant app, not the provisioner this time, but the worker. And as you can see, there is our, I can zoom that, so trust me. Yeah, you can see that it's doing, you maybe don't see that, but it's actually doing the IPXC download. So it's communicating with boots. So if we do Docker compose logs.f now, you will see that there is stuff going here. So the logs from the Think server are saying that a new hardware shows up and it's asking for it's like workflow, or it's downloading the IPXC OZ into the worker. So as you can see, there are stuff ongoing now. And
so that workflow then is not going to be run in on that machine that has it doesn't have an OS installed. It's we're still using that in memory, the OC, the in memory OS.
That's right. Now we are not even executing the workflow. Those logs are just the describing that the hardware is up and it's asking for OZ. So it's downloading OZ. Now it's going to install it, and at some point we will see the actual logs with the hello world image that communicates us that the worker is up and it's asking for work to do. So if we get back here, this is the worker that's still like booting. Now, I don't know if you can see it, but there is the localhost login. So the worker is actually booted a server. So the login by default is root. So we're gonna log in with root, and we are inside. So as you can see from the logs from the provisioner, now there are reference to hello world. So if I look for hello world, now we see that something from the registry downloaded the hello world image. And luckily for us, I hope it is the worker. But now we are inside, so I can do docker ps, and there is nothing like running. But if I do docker ps -a, I see that there is the Tink worker that just ran. And we can also look at the logs for the Tink worker. And it shows that it did something, let's say. So if we get back to the terminal, and we do, this is the vagrant with the provisioner. So if we do again the workflow events, we see that there is a new event here that is state running. At some point, we will see the state successful. I think we won't see it because there is something that didn't work as expected, but that's it. That's the goal. We have the state running. And yeah, probably I'm actually developing Sandbox now with a new feature. So I think I just screwed something. But yeah, I mean, as you get the state running, you will get the action successful event. And that's the life cycle of a worker and of a target machine, I presume. And if we look for, I don't know, we have friends in the community that are working at their own workflow. So if you look for Tinkerbell Ubuntu workflow, there are projects about that. I don't have it top of my head, unluckily, but
you can drop it in the comments later.
Yeah, Alex Hellis made a first one a few months ago, so I don't know how much up to date it is, but it gives you a good vibe. And as part of the Q4, our main goal is to deliver more reusable workflow as possible. And in order to know or follow the development, I think a good way is to follow the proposal repository. Before that, I think this is the last stuff I'm gonna ramble today. I don't know how much time we have. I can ramble all day or week, but I presume people will want to watch the KubeCon keynote at some point, more than myself rambling. And so
come back again later.
Our friend Kim Volk wrote a blog post about how to get Flatcar installed. And Flatcar is really container-centric operating system. So it's also very easy from Flatcar to get Kubernetes up and running. So we are that close to get Kubernetes on Tinkerbell. That close. Look at that. Very small. And so you can get this article. But our plan is to work on the reusable piece of Tinkerbell, because that's why we build that, we open source that, to have workflows, to have actions to reuse. So now that the core is a little bit more stable, we can work on that. So in order to know what we are working on, there is a Tinkerbell proposal repository where even you, contributors from the future, can participate. It's a repository that contains what we want to work on. Obviously, if it's well scoped to a specific service, you can open an issue on the service. But if you are proposing or working on something that is more like community oriented, or it touches Tinkerbell as a whole project, you can have a look at the proposals that are already open. There is also proposals.tinkerbell.org that is the website that renders that repository. So you will see that we have a bunch of proposals, like how to write a proposals. Obviously, it's the first meta one, and it got published and accepted, so it's good. We have another one around how do we want to do releasing, and that's why I'm working at the sandbox, because I'm doing the code. I'm gluing the code that we release binaries as well, because we have people, and I want to run like Tinkerbell data plan, control plan here on my Pi. So I need binaries because containers doesn't run on my old, how old it is. It's a B1 model, 2017. So it doesn't have all the memory that the 4 has. So you can get a vibe of what we're working on from this repo, or you can see at the one that are open here, and you can help us and give us feedbacks. So I recently wrote one about the Tinkerbell Action Hub, that is the reusable website or registry that we would like to develop for actions that are very common, like wiping disk, storing, like downloading operating systems, partitioning disks. Those actions are pretty common when you do a workflow. So we want to serve battle test actions that can be reused. There are others about like default workflow, for example, from Dan, and because a lot of people don't. I mean, it would be cool to have a way to build an inventory of the servers that we don't know about. We don't know that we have yet. So you remember when we did the hardware push action? You can do that if you know that you have a server. But if you don't know that you have a server, you can do the push. So ideally, we would like to serve a default workflow for all the hardware that doesn't have a workflow. In this way, we can register them. So the workflow will look for the MAC address, will look for a bunch of information, and will ship those information to the Tink worker, registering themselves, ready to get the next workflow. That's the idea. So there are a bunch of them over there. So have a look, place a comment, and let us know. And I think I'm done.
Yeah, that was perfect and right on time. I would certainly reiterate the request. If any of this, if you're watching this and any of this is interesting to you, just tinkerbell.org is a great jumping off point. Links to GitHub, links to proposals, links to Slack, YouTube for the other previous videos, and videos and streams in the future. And we look forward to talking with you more about what you're working on. Gianluca, thank you so much for spending some time with me and our future friends today. And certainly I hope you and our friends enjoy both KubeCon and the rest of Cloud Native Con.
Yeah, I'm there at the booth, and there are my colleagues there. So if you want to drop there, see you there. Otherwise, see you on the internet. So thank you for having me.
Perfect. I'll talk to you again later.
Bye.
Bye now.